Things are good?
Yes.
Yes, things are good? Well, that's good. Let's see. Does that work? That's the new homework. All right, so let's talk more about vector spaces. When we started last time. So remember, vector spaces are these objects, for lack of a better word, that we refer to as vectors, and we talk about ways to combine vectors and how we can rescale vectors. So again, your prototypical example is to go back and think about how, if you've done vectors in the past, that's an example of a vector space, right? You got arrows pointing in a certain direction, a certain length, and you know how to combine two vectors together through addition, and you know how to rescale the vector either by stretching it or shrinking it. However, in general, vectors don't have to be those arrows that have a certain length and point in a certain direction. And vectors can be numbers, vectors can be functions, vectors can be matrices, vectors can be emojis. As long as you have them a way to talk about how to combine two vectors together and how to rescale a vector, that could be a vector space. So let's just go through another example of one. It's a little bit stranger, but does turn out to be a vector space. So let's say I'm going to use real numbers as vectors, which is kind of odd. We're going to define x added to y as x times y. Now, notice that I'm specifically writing an arrowhead over the x and y on the left-hand side to emphasize the fact that I'm talking about x and y as vectors in this case. The reason I dropped the arrows and literally just wrote the multiplication is that the vectors here are numbers, and I want to emphasize that when I take x and y, add them, I'm really multiplying. Okay? And if I do a c times x, that's really x to the c power. So we're going to define multiplication as exponentiation, or scalar multiplication as exponentiation here. Again, the reason why I have it on the left-hand side is emphasizing the fact that I'm treating the x as a vector from the vector space. The reason I'm writing it without the arrowhead on the right is because this is really real number exponentiation here, not some vector to a power idea. Ooh, if I can get it, there you go. You're welcome. All right. Notice on the homework that I gave you, with the operations that I defined on there, I had circles around the plus sign and a circle around the multiplication sign. The reason why I did that on there, and I haven't done it so far in class, is that I'm really trying to emphasize on there as well the fact that addition may not really be what you typically think of as addition. Scalar multiplication may not be what you typically think of as scalar multiplication, right? Here, in this example, addition is multiplication, multiplication is exponentiation. So,
and this is specific to this example?
This is just specific to this example, right? You have to have what addition is and what multiplication is defined for you ahead of time. Even though this seems weird, you really already do this, right? Even though you don't really think about it consciously that you do it, you really do this, right? How do you add two polynomials together? What do you do when you have two polynomials? You combine like terms, right? You take the constants, you put those together. You take the x terms, you put those together. That's a different way that you add when you add polynomials than when you add real numbers, right? Because you don't try to put an x and an x squared. They're different entities, so you leave them separated, right? That's a different way of adding than when you add for real numbers, right? How do you add functions in general? If I take an f plus a g, well, you take the y coordinates and you add those two things together, right? You take the y coordinate from the f, you take the y coordinate from the g, and you combine them. But that depends on what the x coordinate is to start with, right? Again, that's a different way of adding than when you just add two numbers together. So you already do this, but you've done it so many times, it's just second nature to think about it, but you really do define addition of different objects differently. Okay? But again, from this perspective, especially when you go back to the polynomials, you can definitely think of polynomials like you add vectors. If I have two vectors and I've written them in components, all you do is just add the components together, right? We've talked about that before, correct? That's your usual vector addition. You can think of polynomials as just being components, right? The first component has the constant. The second component has the coefficient on the x. Third component has the coefficient on the x squared. And all you're doing is just adding components. So again, in that way, you can think of polynomials really being defined as vectors. Because all you're really doing is just adding those components together. Okay? So anyway, my emphasis here again is, like Alex just asked, you have to have these operations defined ahead of time, how you're going to add and how you're going to multiply. Okay. Now, past this section, in most cases, it will be what we're already accustomed to, how we add and how we multiply. But the whole point is that you can make some changes and still have the same properties satisfied. And this is going to be an example of we've made some changes, but all the properties are going to work. Now let's think about why the properties might work before we even go through the proofs here. Think about what your addition properties are. First one is what? Yeah, that's what I'm talking about. Yeah. First one is the very, very first thing we check. Actually, I do need to do one thing on here. I need to make this positive real numbers. I forgot I need to check that, change that. So when I write an R with a superscripted plus there, that means positive real numbers. What's the first thing we need to check?
X bar plus Y bar equals Y bar.
Yeah, when I do the commutative property, has to work, right? I also need to check closure, don't I? Make sure that if I operate the two things together, I land back in the same set. But we have commutative property. Well, how have we defined addition here? As multiplication, which is commutative for real numbers, right? So that shouldn't be an issue. What's the second thing that we check? Or third thing that we check, I guess, technically at that point? Associativity. Again, addition is defined as multiplication. Is multiplication associative?
Yes.
Yeah. What's the next thing?
They're existing as zero vector.
Yeah, a zero vector, right? Now the zero vector acts as what? What's the whole point of the zero vector? What does it act as? Like an identity, right? An identity with respect to the operation. Well, what's the operation really that's going on here? Multiplication, so what's going to be your zero vector in this case? 1, yeah. That's going to go with acting as the identity. The next property is what?
Inversibility?
Yeah, being able to undo the operation, right? Well, how do you undo multiplication by an x? What will you do? Divide by it, yeah, multiply by the 1 over, exactly. So notice that we can start seeing why all of these properties must start to work, at least from the additive perspective, because all we're doing is just using properties of multiplication rather than properties of addition, but they all have the same idea. So let's go through these. All right, so remember again, the first property is closure. What we mean by closure is that if, I'm just restating what closure means, if your x and your y are in your vector space, then x plus y has to be in your vector space, right? And this is just using, I wrote it out in words last time, I think. This time I'm just writing it out in symbols. If x and y are in there, then x plus y has to be in there. So for this property, we're going to let I'm going to ignore the vector hats on these things to start with. If I let x and y be positive real numbers, but when I multiply x and y together, I get a positive real number, right? We agree? So remember, I've switched a little bit here. The property is stated this way, correct? If I start with two vectors and add them together, I land back in the vector space. I get another vector, right? Okay. My vectors in this case are positive real numbers. So I just said let two numbers be positive real numbers, and certainly when I multiply them, because that's how the operation is defined in this case, I get another positive real number. So again, this is the general statement for vectors. This is me putting it in context for how the problem is stated. Does that make sense? Okay, cool. All right. So 2 is commutativity. Commutativity says that, I'll write it this way. If x and y are in your vector space, then x plus y has to be y plus x. That's the axiom, right? So again, I'm just going to state this in terms of the context of the problem. The context of the problem says that my vectors are positive real numbers. So I'm going to start with two positive real numbers. So I'm going to let x and y be positive real numbers. Then xy is certainly equal to yx, since multiplication of real numbers is commutative. Once you get to a point where you are already familiar with the operation, you get to use properties of that operation. Okay? We're already, hopefully, very familiar with multiplying two real numbers together. Right? At some point in your life, you've learned arithmetic, I hope. Okay? So once you get to a point where I'm talking about an operation that I'm familiar with, okay, I'm familiar with real number multiplication. I know that with real number multiplication, I can multiply in either order. That's all I'm stating here. And since that is my operation, I know that my operation is commutative. Does that make sense? All right. Same idea for SochaTivity. I'm going to restate the axiom here. For SochaTivity, it says that if x, y, and z are in my vector space, then I get to regroup relative to the operation. Again, this is the general axiom that I need to show works. I want to change this over to the specifics of the problem. So I need to start with three vectors. In this case, the vectors are positive real numbers. So I need to start with the three positive real numbers. But again, we already know something about the operation in this case. The operation for our vectors, the addition operation, is defined to be multiplication of the real numbers. We know that real number multiplication is associative. So again, I'm just stating that. far, so good? All right. The fourth one is additive identity. And it says that if, oh, sorry, not if, there exists some vector I'm going to refer to as the zero vector such that whenever I add it to the x, I get, or add it to any x, I get back to where I started. So x plus the zero vector is x, the zero vector plus x is also x. Like I mentioned yesterday, all of your axioms besides 4 and 5 really are plug it into the formula, see what you get, right? Even the closure axioms, I'm going to plug it into the formula and see if I end up with a thing that looks like the other ones, right? But for 4 and 5, you actually have to make an identification of something. For 4, you have to identify what the zero vector is. And for 5, given that you found a zero vector, you have to identify what the inverse of an element or a vector is. Additive inverse of an element is, or of a vector is. Okay? So you actually have to make an identification relative to what the operation is that we defined. Okay? Well, you already told me this, right? Because addition here is really just multiplication, so the zero vector is going to be just what? 1. Good. So let's consider 1 in the positive real number. Certainly 1 is a positive real number, right? Notice I'm making the identification. I'm saying this is the thing I think is going to be the zero vector. Okay? Okay.
So despite it being a 1, we still call it the zero vector?
We still call it the zero vector, yeah. Because we still refer to it as, we still refer to the operation as vector addition. Okay. Even though the vector addition really is multiplication. Okay, yeah. Yeah, we still call it a zero vector. I know, it's a little strange. But we still call it that. All right. All right, so then, for any real number x, or any positive real number x, what do we have? Well, if we take x times 1, we get, we get x. Well, except that this really is a vector, though. We're not treating it as a scalar. This is where it's going to get confusing in a minute. Yeah, this is this vector times that vector. I know it's going to get weird in a second. So it's this vector times this vector is really x times 1, which gives me x, right? Which is the same thing as 1 times x. So this is where it's going to get weird in a minute. Right now I'm thinking of 1 as the vector. So this is still multiplying the two together. In a minute I have to make a decision on whether or not 1's going to be the vector or 1's going to be the scalar. So I said it's going to get weird here in a second. We'll talk about it when I get to that point. But right now I'm still just talking about multiplication. So in this case, 1 acts as the zero vector of this vector space. All right, so the next one is about additive inverses. So additive inverses says that given a vector, there has to be something I can operate with the vector to get back to 0, get back to the zero vector. So just to write that down, again, just to write down the general axiom. I'll make sure I remind us of this general axiom idea. So this says, for each x in V, there exists a negative x in V such that x plus negative x gives me 0 and negative x plus x gives me 0. All right, so this always goes, well, by the way, if 4 failed, because we talked about some of the axioms that failed last time, if 4 fails, you can't do 5. Think about why. If 4 fails, I can't get that. I can't get back to 0. If there's not a 0 vector, I can't get back to 0. When 4 failed, 5 automatically fails. Okay? All right. So, in this one, we'll start with a positive real number. I have to get back to what I think is the 0 vector. Well, what I've already shown is the 0 vector, not what I think is the 0 vector. What have we already shown as the 0 vector? 1. What's the operation really that we're doing? Multiplication. So if I start with an x, what do I need to operate with x to get back to 1? 1 over x, right? All right, so then if I have a positive real number, certain if I reciprocate the positive real number, it's still a positive real number. And when we take x times 1 over x, oops, I get 1, which is the same thing as 1 over x times x. I'm going to put it in quotes. That 1 over x is the additive inverse of x in this vector space. Again, right now we're really just playing with what the axioms are, seeing if the axioms are satisfied or seeing if the axioms are not satisfied, so it's not a vector space. Later on, as we actually start doing more and more with vector spaces, our vectors will be the usual kinds of things that you've dealt with. So addition really will be ordinary addition of things. Okay. So that's why we typically use those words. Even though it sounds really weird to say this is the additive inverse. Any questions on those 5? Okay. All right, so then we need to see how scalar multiplication behaves. So we have the second closure axiom, closure of scalar multiplication. So this one says that if x is a vector and c is a scalar, then when we operate the two back together again, I get back in the vector space. Now, again, these vectors that we're talking about depend on the context of the problem. You will be told what the vectors look like, but these scalars are honest-to-goodness real numbers every single time. Okay? The scalars will not change from problem to problem. Scalars are scalars. Okay? Your vectors will be changed depending on the context, but your scalars are always scalars. And if you put two scalars together, it's using the real number operations that put those two scalars together. Okay? So if you have scalar plus scalar, that's regular old real number scalar, or regular old real number addition. If you have scalar times scalar, that's regular old scalar multiplication.
Does C need to be a positive real number, or doesn't matter?
No, so for this, your scalars can be any real number that you want. It has to be anything that you can possibly have. Okay.
And so despite the rules set in place by the vector space that, like, still real number addition is still just regular real number addition, it's not the multiplication.
Correct, yeah. When we're talking about scalar with scalar put together.
Yeah.
Okay, now in this problem, like I said, it's going to be confusing because our scalars are our vectors are also real numbers. So we have to know, which, am I treating it as a vector in the vector space, or am I treating it as a scalar from, I said a scalar. So this one's a little bit more confusing as far as that goes, because the context really does matter here, right, depending on what it is. So this is why this didn't have to be a positive real number, because I'm going to treat this as a scalar, as my, if you will, my lengthening of my vector. This tells me how I make vectors longer and shorter.
Because negative just means you like shrink the vector.
Right, and so in general, the negative means flips the direction for ordinary vector ideas, but for us it really is going to be shrinking it because, well, it depends. If it were negative, it means you're doing a reciprocal. So they will depend on the size of the x too, whether or not you shrink it or stretch it. So, but yeah, it really is, that's our stretching, shrinking factor. That's why it could be negative. All right. So in this case, we're going to let x be a positive real number and c be any real number. Then x to the c is still positive, right? And because I'm doing x to the c here because that's how our scalar multiplication was defined. Okay. But if I take a positive number to any power, it's still going to be positive. By the way, this is why we need positive real numbers for our vectors. If I would have let a negative number be in here, I get issues if my scalar says 1/2. Right? I have issues with closure. It wouldn't necessarily be a real number. So the way I've written the problem before, if I had left the plus sign off and said any real number, I'd have issues. I also would have issues if I try to reciprocate 0. Okay. So the closure axiom here would fail, for instance. All right, so the second one, the 7th and 8th are distributivity axioms. So this is distributivity over vector addition. So this says that if x and y are vectors and c is a scalar, then the scalar distributes over the vector sum. I shouldn't say distributivity of, I should say distributivity over. Sorry. I don't care if you remember the words, I'm just trying to be more accurate. Or maybe perhaps more descriptive. All right. So we start with two vectors in the vector space and a scalar in our set of scalars, which for all of our for our purposes, our set of scalars will always be all real numbers. But again, like I mentioned last time, you could change the set of real numbers to, say, a set of rational numbers or a set of complex numbers. The important part with your numbers is that they all have multiplicative inverses to them. That's what makes these vector spaces. All right, so we want to show that the scalar multiplication distributes over the vector sum, but in this case, the vector sum really is multiplication, and scalar multiplication is really exponentiation, right? Right? This is how x plus y as vectors is defined. And this is how constant times vector is defined, right? So this is c times x plus y in this context. What can I do with this exponent? You can distribute it to each piece. And is that c times x plus, or c times x plus c times y, according to the way it's defined? Yeah. That's it, right? It's literally what we needed. This is why I said a lot of these are just a matter of plugging in the formula and making sure the formula works, right? So since I have multiplication of real numbers, I know that exponentiation distributes over multiplication. Not any issues. All right, 8 is distributivity over scalar addition. So you start with one vector and two scalars. Then the scalar multiplication distributes over the scalar sum. Again, I emphasized this on Monday, but I want to emphasize it again. These two plus signs mean two different things. Okay? What's being added here? Scalars. So this plus sign, no matter what, represents regular old real numbers addition. This literally is take C and D as real numbers, add them together as real numbers. Okay? Nothing funky there. What does this plus sign mean?
Multiplication.
Well, for this context of this problem is multiplication, right? In general, you're adding what kind of objects? Vectors, right? So this is regular old real number addition. This is addition dependent upon how it was defined in the problem. Vector addition. Just like Jack mentioned, it's multiplication in this problem. Right? Yeah. So make sure that those two things, you keep those two things in mind. Even though we use the same symbol, they mean different things in this case, which is why sometimes I emphasize the difference between the two by putting a circle around my plus sign for vectors, to denote that I really am adding two vectors rather than two scalars. Okay. All right, so what is the left, when we do this for the context of this problem, oops. When we do this in the context of this problem, what does the C plus D times X look like? Good. That's exactly right. Again, the scalar multiplication is exponentiation, right? So we're going to take the scalar, C plus D, and put it up in the exponent. Okay. All right. Now, everything here now is your regular old real number operations that you've always done. I've got a plus sign and an exponent. What can I do? Yeah, we can break it into those two pieces, right? This is one of our laws of exponents. What is the right-hand side of this equation now? In terms of the context of the problem, what is the right-hand side? This is exactly what we need, right? This is C times X, right? According to the definition of the problem, this is C times X, this is D times X, and what have we done with those two vectors? Added them, right? So that's literally what we need for the context of this problem, right? This is an associativity property. It's not quite associativity because it's two different operations, but I still call it that. So this says that if I have a vector and two scalars, I can do a regrouping idea. Again, just to emphasize, like I emphasized in the previous axiom, what kind of multiplication are we doing here? This is scalar, well, this is multiplication of two scalars, right? It's real number multiplication, right? This is, just like this was regular old addition, this is regular old multiplication, like you always take two numbers and multiply them together, right? What are the two multiplications going on here? Yeah, there's a vector operation, right? The scalar times a vector gives me a vector, another scalar times a vector. So they really are, honest to goodness, different operations here. Okay. All right, so same idea here. What does CD multiplied by X look like by our definition?
X to the CD.
Okay. And now I have multiplication up at my exponent. So what can I do to make it look like what the right-hand side is supposed to look like?
X to the D to the C.
Good. Yeah, X to the D to the C. Because what is inside the parentheses here relative to the problem? This is, yeah, D times X, and then this is C times that same vector. Right. So again, this is using what we already know about real number exponentiation, and then in the context of the problem, we're good. All right, last one. The property is really that we have a unitary idea. Don't worry about the fact that what the word I'm using, but that's the idea. We want to make sure that if we multiply, it's a scaling property. It's what we call them scalars. If I take the scalar 1 and multiply by a vector, should it change its size?
No.
No, because it has a scale of 1 already, right? So this one is if x is a vector, then 1 times x is x again. Multiplication by the number 1 should not rescale the vector to a different size. It should have the exact same size. It should be the exact same vector. There should not be any rescaling going on. All right. So let's let x be an r plus. All right. So this is why I said it was weird. In axiom 4, we treated 1 like it was a positive real number that was our vectors, right? In axiom 10 here, this 1's not a vector. We're not treating it as a vector, we're treating it as a scalar. Okay? So how do we do 1 times x in this case? X to the first, right? And we really do get x back again. So we really do have a vector space.
What's an example of one where the unitary fail?
That was the example we did last time, where a scalar multiplication was double what your scalar was.
Oh, yeah.
Yeah. So just say whatever the scalar was, double it. So that would make the scale fail. All right. Questions about this? I know this is weird. That's why I'm taking time on it. I know it's weird. Okay. It's cool. I think it's fun, but it's still weird. All right. They've got lots of different examples in the book as well. So for practice, and I gave you the extra practice problems last time as well and posted those on Moodle with answers. So you got lots of practice with these, I hope. So I would expect that you'll practice for next time. I've got a couple of proofs I want to do for the end of this section. But I expect that you practice these and come with questions next time if you need to see some extra examples. I know it's weird. I know it's a lot to get your mind wrapped around because we really are doing abstraction here, right? All right. So one of the things that we are interested in with vector spaces is things that all vector spaces have in common. No matter what happens, no matter how you redefine your addition, no matter how you redefine your scalar multiplication, we want to see what kinds of things, what kinds of properties all vector spaces have to have in common. Okay? So this is theorem 5.1.1 in your book. So we're going to let V be a vector space. Anytime, by the way, I will be consistent with this. Anytime I use a capital letter V, assume that I'm talking about a vector space, even if I don't explicitly write down that it's a vector space. I'm not going to use the capital, unless I say determine whether or not V is a vector space, you can assume that it means a vector space. Okay? So we're going to let X be a vector space. Let's let X be a vector in V. And let's let C be a scalar. Then we got four things that you would expect to be true in general. If I take the scalar 0, that's certainly a real number, and multiply it by the vector x, what vector would you expect to get out? I would expect to see the 0 vector, right? Likewise, I'm going to write this off to the side. If I take any scalar and multiply it by the vector 0, what do I expect to get out? The 0 vector again, right? I would expect both of those things to happen, wouldn't I? Now, one of the reasons why I wrote them side by side is because the proofs look very, very much the same. When I do proofs like these, I want to make the left-hand side, I want to make one side look like the other, right? I don't know it's an equation yet, so I can't operate on both sides. So I want to make it look like, I want to make one side look like the other, or I can start with make a true statement. So I'm just going to put a bar under here just so I can see what's going on. All right. We're going to use a tried and true trick that you've done ever since probably you started learning how to add fractions. You're going to do clever rewritings of numbers that you already know properties of. So for example, when you learned how to add fractions, you did clever rewritings of 1 to get common denominators, right? Right? If you needed if you say you wanted to add 1/3 and 1/4, you'd multiply the 1/3 by 4/4. Right? 4/4 is a clever way to rewrite 1, for example. Other clever rewritings are clever rewritings of 0. Okay? So one typical clever rewriting of 0 is just to rewrite 0 as 0 plus 0. Okay. Why does that help us in this case? I'm going to go through this in a little bit more detail. Why does this help? What can I do on the right-hand side now that I couldn't do on the left-hand side before? Well, I've got a plus sign here and scalar multiplication here. What can I do? I can distribute, right? I can take 0x plus 0x. This is by your axiom number 8, right? Right? Okay. What am I trying to get on one side here? Just a 0 vector, right? So what do I probably want to do? I probably want to move this over to the other side, right?
Yeah.
How do I get rid of this? Subtract it, or subtraction really is doing what? Adding the additive inverse, right? So if I have 0x plus the negative of 0x, that's the same thing as 0x plus 0x plus the negative of 0x, right? What axiom tells me I can do this? In particular, what axiom tells me that I know that I have a negative 0x? 5, right? That's the one that has to do with additive inverses. Oops. Right? And again, the reason why we chose 0x, or negative 0x, is because what do we get on the left-hand side now?
0.
The 0 vector. We're not quite to where we need to be on the right-hand side. What do I need to do first before I can get to what I need on the right-hand side? I actually technically have 2 more steps to go. What do I need to do first?
Switch around.
Switch around.
The inverse with one of the 0 vectors.
So you mean regroup?
Yeah, regroup.
Okay, good. Okay, that's what I need. All right, so this left-hand side was another consequence of axiom 5 here, right? That was the whole reason why we chose the negative, the additive inverse. What axiom allowed me to do this one?
3.
That one's 3, right? That's the associativity.
Yes.
Okay. And then inside the parentheses again, we get 0, and that's our axiom 5 again. And now what do we get on the right-hand side? Just 0x, correct? And that's axiom, which one? When we add the 0 vector, we get back to what was started? 4, yeah. Again, like I mentioned, this is one of the reasons why solving equations for children is difficult. There's a lot of hard stuff going on in doing something like this. Right? Think about it, you've never, well, I mean, you haven't seen necessarily this proof before, but think about it, you've never seen solving equations before. And you got all this stuff that you're trying to undo and move to other sides and all of this stuff. There's a lot of abstract concepts. All right, you would do, I'm not going to go through it right now because of time, but how do you think you would start number 2? The same way. I would take c times the 0 vector and rewrite it as what? Good. Yep, exactly. And do the same kind of proof. Exactly right. All right, the other 2 properties that pop up, and I'm just going to write down the properties and not prove them right now. If you take negative 1, if you take the negative 1 times a vector x, the number negative 1 times a vector x, you should get the additive inverse of x. And the last one says that if c times x is the 0 vector, then either c is 0 or x is the 0 vector. So those are the last 2 properties. So anyway, just as far as proof techniques goes, this one, start with taking x plus the negative 1 times the x and see what happens. This one, is since you're trying to prove an either or, assume that c is not 0 and show that x has to be 0. So, all right. We'll talk about those next time as well as to get into section 5.2. But again, practice some of these vector space problems so that if you've got questions, you can ask them Friday. Okay? All right. Have a good one. We'll see you then.